So hello. Today I'm going to talk about Cauchy's Ridgity Theorem. So it's really quick, just about Augustin Cauchy. He was a French mathematician in the 1700s, and he found and proved many theorems concerning calculus and analysis. Today we're going to look at his geometrical proofs. So here's the theorem. So basically, if we have two 3D convex polyhedrons, and if they have the same connections, so if they're combinatorially equivalent, and they have congruent faces, then they must have equal angles. And therefore, the two polyhedrons will be congruent. Just really quick to define combinatorially equivalent. So any two objects, in this case we're dealing with polyhedrons, where the connections between the elements, in this case the vertices, are the same, then they are combinatorially equivalent. So if we have this shape here, so we have connections A to B, B to C, C to D, D to E, and also A to D. If we have the same vertices with the same connections, then they will be combinatorially equivalent. So for example, we have this, or this, or this. So all of these have the same connections and the same vertices, so therefore they're combinatorially equivalent. So just to help visualize this theorem, if we imagine this metal 3D polyhedron, so where the faces are like a plate, a metal plate, and the edges are hinges, so they allow movement. So the theory states that even though this metal polyhedron has hinges which allow for movement, it will not be able to actually change shape, that it will be stuck in that position. Another way to visualize this is with nets. So we may have done nets back in junior high school. And basically, this is showing that the nets are unique to a 3D polyhedron. So all the connections will be the same, and we'll have the congruent faces. The faces won't change, so they'll be unique. So we're going to talk a little bit about the proof of this. To prove it, we're going to go through three different lemmas. So the first one we call the arm lemma, and then we kind of deal with the sign change lemma, and then a color lemma at the end. And actually, in his original proof, he made a mistake by not considering concave polyhedra. If you remember, the theorem requires the two polyhedra to be convex, because this will not be true for concave. So for example, this case. Here you can see that the faces will be congruent, but the angles are different. So you can see they switch from concave to convex. So we will require the convex requirement. So let's start with the arm lemma. So we're going to have two convex planar or spherical polygons. These will go for spherical as well. And we're going to label them as such, so Q1 to Qn. And then we'll have another one as well, right, with Q1 prime. And all the lengths except for one will be equal. So Q1, Q2 will equal Q1 prime, Q prime 2. As well, the angles, so from alpha 2 will be less than or equal to alpha 2 prime. And this will be all the true up to an minus 1. So if we have that condition, then Q1 to Qn will be less than or equal to Q1 prime to Qn prime. And if they're equal, then the two polygons will be congruent. So to help visualize, we have this little picture. So if you look on the left, we have the polygon P. We have Q1 to Qn. And you can see I drew the Q1 to Qn is a red dotted line. And we're going to change this. We're going to basically create a new polygon, so P prime. So all of these side lengths will be the same. Actually, all of the angles will be the same except for the alpha n minus 1. This will have increased. And as you can see, the red dotted line also increases. So this will just be a quick visualization of the arm lemma. Now the proof of this will be, there's various proofs. Cauchy did it with induction. We're not going to go through the proof because it's quite long and complex. If you want, I have the data so you can see the proof. But we will kind of skip over it for today. So the second proof second lemma we'll go through is the sign change lemma. This is going to be a corollary of the arm lemma. So this is kind of the main thing we'll be using. So again, we'll have the two convex planar, or spherical polygons. And this time we'll have all of the sides the same length. And then when we go from polygon P to polygon P prime, we're going to assign a plus or minus sign where the internal angles increase or decrease. So this lemma will state that there's either at least 4 sign changes going from P to P prime, or there are no sign changes at all, and P prime are congruent. So here's a kind of, again, an example of the idea. So on the left, we have just this polygon, this quadrilateral. And then on the right, we have the same quadrilateral, a quadrilateral with the same side lengths. But the angles changed in that fashion. So this is actually a rhombus. And as you can see, for angle A and angle C, they both increased, and angle B and angle D decreased. So this is one example of the assigning the signs. And again, the lemma states that there must be at least 4 sign changes going from P to P prime. So we can't have 1 or 2 or 3. And again, if there's none, they will be congruent. So we can go through the proof. This will deal with the previous proof we talked about. So this will be a proof by contradiction. So we're going to do it in 2 parts. The first part, we're just going to assume there's only one change in sign, so either positive or negative. Now if you remember the arm lemma, if one of the angles increases or decreases, then one of the sides must also increase length or decrease length. But by our assumption, all of the side lengths stay the same. So this is a contradiction, as one of the sides can't increase, but the angle does. And in case 2, we're going to do 2 or 3 sign changes. So below, you see on the left there's a polygon. This has one increased angle and one decreased angle. And the polygon on the right has 3. So in this example, it has 2 positive and 1 negative. Now, if excluding this example, if one polygon had 2 or 3 of all of the same, so for example, if they're all positive increased or all negative, then the same arm lemma would apply, where if all of the angles increased, then one of the sides must also increase. And again, this can't be true because it contradicts our assumption. But say they're different. So again, on the left one, we have 1 positive and 1 negative. So we can create the line segment, so connecting kind of in between the 2 edges, kind of separating the angles, so separating the positive and negative angle. You can see it's very easy to do for the left side. On the right side, it can get a bit tricky, but we'll always be able to create this line segment as the polygon, again, is convex. So no matter the way, we should be able to create this line segment. So for both these cases, if you apply the arm lemma, which we discussed before, so for example on the left polygon, if we apply the arm lemma to the right side, that red line segment must increase. Because one of the angles increases, the side length also must increase. But if you apply the arm lemma to the left side, the line segment must decrease. Because one of the angles decreases, that red dotted line also must decrease. This is the same for the polygon on the right. So because we have one side saying the line must increase, and one side saying the line must decrease, this is a contradiction. So 1, 2, or 3 case sign changes don't work. As we showed in the beginning, we do have an example with 4. Therefore, there must be at least 4 changes. We'll go through this. This must be at least 4 changes. So the last lemma we're going to go through is the color lemma. It's going to be slightly different from the other two, as this is going to talk about planar connected graphs. But again, we're going to be talking about a change in color. We're not going to go through the full proof for this, but kind of introduce it. So for the theorem, we'll have G be a connected plane graph with n vertices. This is similar to what we did in class. Now, if the edges of G are two-colored, so that all of the edges will be colored with either, for example, black or white, then there is a vertex of G with no more than 2 color changes in the cyclic order. So if we count the changes, so for example, looking back here, so if we look at the top one, the vertex changes color 4 different spots at the arrow. So when you go around, if you start from near the top, it goes from black to white, so that's 1 change, then white to black, and then black to white, white to black, and then black to black again, so no change. So there's a total of 4 changes. So again, this theorem states that there must be at least 1 vertex with no more than 2 color changes. So again, looking at this, if you look at the center, it has 4 color changes, which doesn't match. But the 3 on the outer side, on the left, have 0 color changes, so those would fit the theorem. So to prove this, we have to come up with a few definitions first. So we're going to start by defining a new, just kind of a clarification of the face. So we're going to start with a K face. So a K face will be a face surrounded by K edges. And then we're just going to let the number of faces of a graph be F and the number of edges be E. So we can create some equations for this. So if we have F1, F2 up to Fk, and then all the way up to Fn, these are faces of the graph. So they're connected to the K vertices. Then F, the total, again, the total number of faces will be F1 plus F2 all the way up to Fn. So this should make sense. We're just adding up the faces. But we can also come up with an equation for the edges. So each K face will have K edges surrounding it. So for example, if you have one 3 face, then that face will have 3 edges. So if we multiply the number of faces, so the K face by K, and then add those all up, we'll get 2 times the number of edges. This is because for each edge, there'll be 2 faces. So it's basically counting the edges twice. So it'll be double E. Again, this is counting the overall planar the infinite plane as a face as well. So again, looking back here, if you look at the top picture, there's one two-face, and then there's one five-face, the outer one. So we're going to, again, prove this by contradiction. So we're going to assume that no vertex will have at most two changes. And there must be an even amount of changes as we go around the vertex. Because when we start, we usually start with like a black edge or a white edge, and we're going to end with the same color edge. Because we start and end with the same edge as we go around, there has to be an even amount. If there's an odd amount, we'd end with a different color. So if we have no vertex with at least two changes, then all vertices must have more than two color changes. And again, since they can't be odd, they'll have to be 4. So we're going to say all vertices have to have at least 4. So we're going to see be the total number of color changes. So the total number of corners where the color changes. And then again, so since each vertex must have at least 4 color changes, C will be greater than or equal to 4n. And basically, using the equations we had before, we can create these various equations. So what we're going to do is we're going to count the number of faces and count the number of color changes. And again, using the idea that they have to be even. So, for example, the 7 face can only have a total of 6 color changes. It can't have 7. And then just by rearrangement, so if you see the bottom equation, that looks very similar to the number of edges. Again, we do not have F1 or F2. We do not have a 1 face or 2 face, because those would have 2 or less color changes, which is contradictory to our assumption. So for this case, we'll start with F3. So combining it all together, we get 4n is less than or equal to 4e minus 4f, which we can rearrange to n minus e plus f is less than or equal to 0. Now from Euler's formula, which we learned in class, we know that n minus e plus f should equal 2 for a connected planar graph. Therefore, this contradicts Euler's formula. So that's the proof of that. So now with these 3 lemmas, we should be able to go through the final proof. So again, the proof is the theorem is if all of the faces are congruent, so all of these various faces are congruent, then all of and going from the angles, that this will be rigid, so there'll be no movement between this polyhedron. So again, we'll start with this. So if we have the two polyhedrons, which will be convex with congruent faces, so we're going to start by coloring the edges. So if the interior angle between the adjacent faces increase, then we're going to color it black, and if it decreases, it's going to be white. This is going to create this 2-colored plane graph on the surface of P. And we're going to transfer to a unit sphere using this radial projection, this idea of radial projection. And then from our color lemma, we know that for some vertex P, at least one, that there's at most 2 changes between black and white edges. And again, it has to be adjacent to at least one black or white edge. So for example, if you see this picture, here is one example. The color lemma shows that this point P must exist, where there's only 2 color changes at most. So what we'll do next is we're going to intersect point P with a sphere. A small sphere of radius epsilon. That's going to be centered at vertex P. And we'll do the same with the second polyhedron. So by intersecting these, we are going to get these convex spherical polygons. And we're going to call them Q and Q prime. And these arcs and the corresponding arcs will have the same lengths. So again, intersecting this point P. So now we're going to get, if you look on the bottom, we're going to get this graph. So then from here, we're going to mark by a plus the angles of Q for which the corresponding angle in Q prime is larger, and again, minus if it's smaller, and nothing if there's no change. So again, looking back here, we had the 2 blacks and 1 white, so there's 2 decreases and 1 increase. So we're going to write it similar to this. And again, from our choice in P, we know that there's some plus or minus signs. So we didn't choose a P with absolutely no signs. And again, from the color lemma, that there must be 2 changes. And again, here we can, from F with at most 2 changes. So going from here to here. Now from our corollary, so the second lemma we had, the number of changes in sign must be at least 4. But this leads to a contradiction with the color lemma, as we said there is at most 2. So based on this, there can't be any changes in angles, and therefore P is congruent to P prime. So again, by the contradiction. Yeah, thank you for listening. That's all.